This video demonstrates velocity and displacement calculations. A cyclist rides their bike to and from work each day. They live 9 kilometres northeast of their workplace. There's a bike path which takes them directly there, and it takes approximately 40 minutes each way. The first thing I want to do is draw a diagram that represents the scenario here so that we have a fuller understanding of what's going on. So the cyclist lives 9 kilometres north east of their workplace. So if their house is here, then their workplace is going to be in a southwest direction. That's their workplace. Here we go. And draw a bicycle. There we go. Okay, so this distance is 9 kilometres according to the question there. So first we're being asked to calculate the cyclist's displacement for their journey to work, just to work. So displacement is a vector quantity, meaning we need to include both magnitude and direction. So the magnitude is pretty simple. It's going to be 9 kilometres. They started at home, they travelled 9 kilometres to get to work. So our displacement, the magnitude component, is going to be 9 kilometres. And this is the part that might be just a little bit confusing, so you don't want to trip up on the language being used. They live northeast of their workplace, which means that they have travelled in a southwest direction. So their displacement for their journey to work is 9 kilometres southwest. And I'm just going to put a box around that to show that that's our answer to the first question there. Next, we're being asked to calculate the displacement for the whole journey. We want to remember that, like I just said, displacement refers to magnitude and direction. If the whole journey involves them starting at their house, going to work, and then ending at their house, that means that they've finished where they started, and so they haven't moved in a particular direction, which means that displacement is going to be equal to 0. Next, we're asked to draw a position time graph for their whole journey. So we're going to have our X and Y axes. The Y-axis is going to be displacement, the X-axis is going to be time, and I'm actually going to convert the measurements that I've been given into into meters and into seconds. So 9 kilometers is going to be 9,000 meters, and 40 minutes is going to be 2,400 seconds. 40 minutes times 60 seconds per minute is 2,400 seconds. So if we have a look at our x-axis first, so it takes him 2,400 seconds, or it takes the person 2,400 seconds to get to work, and then they turn around and they come back. So halfway through their journey, 2,400 seconds, they turn around and come back. So the total journey is going to take 4,800 seconds. The first leg of the journey, they're travelling 9,000 metres from their house. So let's go 2, 4, 6, 8, 10. Which means 9,000 will be approximately here. So what happens is they travel that distance and then they turn around and end where they started. So that's going to be our position time graph. Part D, calculate the velocity for their journey to work. So let's have a quick look at the top of this slide. Velocity is equal to a change in position over time. So that's the formula we're going to want to use. Velocity is equal to a change in position over time. we have been, and we're looking at just the journey to work again. So we've actually got the information that we need right here. The distance travelled is going to be 9,000 metres over a period of 2,400 seconds, which gives 3.75 metres per second in a southwest direction. And we'll put a square. Okay. And our last one, calculate velocity for the whole journey. As I've said previously, velocity is a vector quantity, so we're talking about magnitude and direction. And as we talked about in part B, when I said that displacement is also a vector quantity, therefore we've finished where we've started, and so displacement must be equal to 0. We can say the same thing about velocity here. There is no change in direction. There is no directional change because they've finished where they started.